Today we're looking at properties of parallelograms. We're going to prove theorems about parallelograms and use relationships among sides, angles, and diagonals of parallelograms. Let's talk about the definition of a parallelogram. A parallelogram is a quadrilateral with both pairs of opposite sides parallel. The term parallelogram, ABCD, can be abbreviated as we just draw this little parallelogram and then ABCD. Our first theorem is the parallelogram opposite side theorem, and we will prove that in example 4. If a quadrilateral is a parallelogram, then its opposite sides are congruent. So AB would be congruent to CD, and BC would be congruent to AD. The parallelogram opposite angles theorem says if a quadrilateral is a parallelogram, then its opposite angles are going to be congruent as well. So angle A will be congruent to angle C, and angle B will be congruent to angle D. The parallelogram consecutive angles theorem says if you have a parallelogram, then its consecutive angles are supplementary. So that just means supplementary, remember, it means it adds up to 180 degrees. So A plus B would equal 180, B plus C will equal 180, C plus D will equal 180, and D plus A will equal 180. And we will go ahead and we will prove that in example 5. The parallelogram diagonals theorem says if a quadrilateral is a parallelogram, then its diagonals bisect each other. That means they cut them in half. So AM will equal MC and BM will equal MD. So all of these are parallelograms, and we're going to find the variable. So these two are right next to each other, so they're supplementary. Supplementary means it adds up to 180 degrees. Remember that if you have an S, it changes into an 8 for 180. So 2x plus 116 equals 180 degrees. We're going to minus 116 from both sides of the equal sign. We have 2x equals 64. So 2 times some number x equals 64, so we divide by 2 and we get x equals 32. Both of those will be 32. So x will equal 32. Now on 2, we have some angles that are opposite each other. Parallelograms have equal angles that are across from each other. So y plus 21, or y minus 21 equals 121. We add 21 to both sides, and y will equal 142. Now, in a parallelogram, the opposite sides are also equal. So 17 will equal x minus 8. We add 8 to both sides of the equal sign, and x will equal 25. On example 3, we have a parallelogram, and parallelogram diagonals bisect each other. So x plus 2 is going to equal 8. I'm going to subtract 2 from both sides of the equal sign, and x will equal 6. I also have 5y will equal 15. I divide both sides by 5, and y equals 3. On example 4, I'm going to do a proof. I'm going to prove the parallelogram opposite sides theorem. So if a quadrilateral is a parallelogram, then its opposite sides are congruent. We're going to do a 2-column proof today. We have our statements and reasons. So we start with the given information. We have parallelogram ABCD, and the reason we have that is given. And we're going to use, the only thing we have is a parallelogram, and so we're going to use the definition of a parallelogram to say BC is parallel to AD, and AB is parallel to CD. And for reasons, we just put definition of a parallelogram. That's what a parallelogram is. It means that both of the opposite sides are parallel. Well, since we have parallel lines, we can use a transversal. And I've got this orange transversal in here. If our yellow lines are the parallel lines and the orange is the transversal, we can show that 3 is congruent to 2 and 1 is congruent to 4. The reason is the alternate interior angles theorem. Alternate interior angles are congruent whenever a transversal is cut to sets of, or a set of parallel lines. So now we've got two angles that are the same. We want to show that middle part is the same. AC is congruent to CA by the reflexive property. Now we can show that these two triangles, triangle ABC is congruent to triangle CDA. And the reason for that is because of angle side angle. We've shown two angles are the same and a side in between those two angles. So now we can show that AB is congruent to CD and BC is congruent to DA, because if those triangles are congruent, then the corresponding parts of the congruent triangles are congruent. On example 5, we're going to prove that consecutive angles are supplementary. We are given parallelogram ABCD. So remember, a parallelogram, the definition of that is that you have two sets of parallel lines. So we have BC is parallel to AD, and we also have AB is parallel to CD. Now I have a transversal. I'm going to pull this AB down and have it be a transversal. Well, angle A and angle B, they are same side interior angles. So same side interior angles add up to 180 degrees. So we just write same side interior on the reason. Now I'm going to draw another set of parallel lines here. B is also parallel to CD. So I'm going to write AB is parallel to CD, and the reason would be, again, the definition of a parallelogram, because because you have a parallelogram, both sets of opposite sides are equal. You could have also written this up when you did the BC and AD. Now, if we have this orange transversal, AD, I know that angle A and angle D have to add up to 180 degrees because they are same side interior angles. So the same side interior angles theorem tells us that those two add up to 180 degrees. So since we have the measure of angle A plus the measure of angle D equals 180, then A has to be supplementary to D, and we've already shown the measure of angle A and B add up to 180, so those are supplementary as well. Example 6, prove the parallel diagonals theorem. So if it's a parallelogram, then its diagonals bisect each other. We're given parallelogram ABCD. And so when it's a parallelogram, we're going to use that definition of a parallelogram to show that use our same side interior, alternate interior angle theorem. Usually when we have parallel lines, that's what we do. So AB is parallel to CD and BC is parallel to AD. And that will just be the definition of a parallelogram. I have a transversal AC. So angle 1 and angle 4 are going to be congruent because they are alternate interior angles, alternate interior angle theorem. And BD is also a transversal, which would make angle 2 and angle 3, they would both be congruent. And again, that is also by the alternate interior angles theorem. AB is going to be congruent to CD. And the reason for that is what we just proved a second ago, the parallelogram opposite sides theorem. So those two sides are the same. And so triangle BEA has to be congruent to triangle DEC because we have angle, side, angle. We've shown two angles are the same and the side in between. So since we have shown that, we know BE has to be congruent to DE and AE has to be congruent to CE. And the reason for that would be CPCTC. So corresponding parts of congruent triangles are congruent. AC and BD bisect each other. And that would just be the definition of a bisector. That's what we're trying to prove. Now, we have three vertices of triangle WXYZ. They are -1, -3 is W, -3, 2 is X, and 4, -4 would be Z. We need to find the third vertex. So notice, look at W to Z, and it goes down 1 and over 5. So that's the slope, is -1/5. So we want to find the slope of the top is going to be the same as the bottom. It's going to go down 1 and over 5 as well. So we have the point over 2, up 1. On example 8, we have the vertices of parallelogram QRST. We have Q at -1, 3. R is at 5, 2. S is at 1, -2. And T is at -5, -1. So we are going to find the coordinates of the diagonals. Now, when I cross these, it's not at you can't really tell where it is. So I'm just going to use the midpoint formula to get a perfect point. Remember, to find the midpoint of two lines, we average the x's and average the y's, x1 plus x2 over 2, and y1 plus y2 over 2. So let's do Q and S, x1, y1, x2, y2. We add the x's, -1 plus a 1, divide by 2. And for the y's, we have -2 plus 3 over 2. -1 plus 1 is 0, divided by 2 is still 0, and -2 plus 3 is 1/2. And notice that makes sense. It looks about like it 0, 1/2. So I can do it with the other two, and I get 0, 1/2 as well. -5 plus 5 is 0, divided by 2 is 0, 2 minus 1 is 1/2.